Hello everyone, I'm Varsha studying Computer Science and Engineering in Sri Venkateshwara College of Engineering. Today's video is about vector calculus, basic vector operations, gradient, divergent of vector field, curl of vector field, Stokes theorem, application of vector calculus in physics, application of vector calculus in engineering, conclusion. Vector calculus. Vector calculus is a branch of mathematics that deals with calculus for functions of more than one variable. It is important for many engineering, physics, and applied mathematics fields. Vector calculus provides powerful mathematical tools to study physical phenomena. Basic vector operations. Vector addition. Two vectors can be added together to form a resultant vector. The resultant vector is a vector that connects the origin to the end point of second vector. Vector subtraction. Two vectors can be subtracted from each other from a third vector. This is calculated by adding the negative of the second vector. Vector multiplication. Vectors can be multiplied in two ways, dot product and cross product. Dot product gives scalar quantity and cross product gives vector quantity. Gradient. The gradient of a scalar function is a vector that points in the direction of maximum increase of the function. It is important for optimization problems. Physical interpretation. In fluid dynamics, the gradient of the velocity field is used to calculate the pressure field. Example, temperature gradient in the metal plate under certain thermal conditions can be calculated using vector calculus. Divergence of a vector field. The divergence of a vector field is a scalar quantity that measures the source or string of a field. It is important for fluid mechanics and electromagnetism problems. Physical interpretation. Divergence is used to calculate the flow of fluid in porous media like oil reservoirs. Example, flow of air through aircraft engine can be analyzed by calculating the divergence of velocity field. Curl of the vector field. Curl of the vector field is a vector that measures tendency of a field to rotate around itself. It is important for fluid mechanics and electromagnetism problems. Physical interpretation. The curl is used to study motion of fluids with eddies and vetroties. Example, formation of vetroties in wake of a moving vehicle can be predicted using vector calculus. Stokes theorem. Stokes theorem relates the curl of the vector field to the circulation of the same field around a closed curve in space. Formula. Stokes theorem states that surface integral of the curl of a vector field over a surface S is equal to the line integral of same vector field around the closed curve loop C that bounds S. Application. Stokes' theorem is used in electromagnetism for calculating magnetic fields around the circuits and in fluid mechanics for calculating fluids around the obstacle. Green's theorem. Green's theorem relates the curl of two-dimensional vector field to the line integral of same field around closed curve in a plane. Formula. Green's theorem states that double integral of the curl of a vector field over region R is equal to the line integral of same vector field around the boundary R. Applications. Green's theorem is used in physics, engineering, and fluid mechanics to calculate fluxes and work done by conservative vector fields. Application of vector calculus in physics. First, in electromagnetics, vector calculus is used extensively to study the behavior of charged particles, electric and magnetic field. Next, in quantum mechanics, the mathematical formalism of quantum mechanics heavily relies on vector calculus concepts and operators. Next, classical mechanics. Vector calculus is used to formulate the laws of motion for particles and rigid bodies. Fluid mechanics. Vector calculus is used for calculating fluid flows around the obstacles like wings, cars, and boats. It is important for aerospace engineers and naval architects. Wave theory. Vector calculus is used for calculating the behavior of waves in oceans and rivers and lakes, and it is important for coastal engineers and marine biologists. Applications of vector calculus in engineering. Civil engineering. Vector calculus is used to study the properties of fluid mechanics, heat transfer, and structural mechanics. Structural analysis. Structural engineers use vector calculus to optimize bridges, dams, and high rises for safety and maximum efficiency. Fundamental forces. Vector calculus helps civil engineers to analyze the fundamental forces that act on the structure and material, optimizing their strength and stability. Mechanical engineering. Designing machinery, vector calculus is used to model the motion of gears and claims, optimizing their performance and reducing noise. Wind turbines. Vector calculus helps in design blades to optimize wind angle, blade twist, and airflow to maximum output. Roller caster design. Designers use vector calculus to analyze forces and designs to stimulate the specific sensations. Aerospace engineering, space missions. Vector calculus is used to model and optimize population and aircraft trajectories in a orbit space across the solar system. Aeroplane design. Vector calculus helps designer to increase the efficiency of aircraft and reduce fuel consumption and environmental pollution. Biomedical engineering, musculoskeletal analysis. Biomedical engineers use the vector calculus to complex model structures to detect and treat the musculoskeletal and cardiovascular disease. Qualitative physiology. Vector calculus helps researchers to study biological processes describing the flux of a substance in time and space and temperature. Conclusion. Real-world application. Vector calculus is a powerful tool that enables us to understand natural world better. It has numerous applications including predicting weather patterns, designing aircraft, and creating computer graphics. Vector calculus is essential for many fields of science and engineering, from quantum mechanics to aerospace engineering. Thanks for watching the video.